Okay, let's get started. We're going to review what we learned last week. First of all, we're going to look at what is synchronous serial communications and also what is asynchronous communications. In fact, it is very important to understand the difference between these two, because here, as you see here, in the synchronous communications, we have a clock pin. We have a clock in addition to the data and ground. Whereas asynchronous serial communications, we have a data and ground. We have no clock in this case. What we are using typically in 8051 is going to be asynchronous communications. And in fact, this kind of serial communications exists in every single microprocessor. If you use the ARM processor, AVR, and any other processor, you may hear about the UART. People call this serial communication as a UART. Okay? If you go to industry, everyone just call this one as a UART. Universal Asynchronous Receive and Transmit. I think that's probably what it stands for. So the UART is a general terminology that everyone call this. Okay? So you probably want to remember this terminology, UART. So this is UART, but when we talk about UART, typically we call this one asynchronous serial communications. This looks like a nice because it has a clock, but certainly having a clock pin is a problem. Because here, let's see, since we have a clock, right? If you have a very large distance between the transmitter and receiver, let's say transmitters are here, and let's say receiver is in another room. So the distance between these two, say, is like 100 meters. In that case, you transmit a clock, like a pulse train, but the distance is like 100 meters, so these clocks will die out. It doesn't reach the receiver, right? Because this is too long distance. The clock is not going to be delivered to the receiver. Certainly, this is a problem. And not only that, the clock, in fact, is a rectangular pulse, which is not really good for transmission. So we have many problems to deliver the clock. So therefore, it is more efficient, and it is also more cost-effective to use this asynchronous serial communications. However, the problem in asynchronous serial communications is that we have no clock. So as I said earlier last week, let's say we have a transmitter and we have a receiver. Let's say transmitter wants to transmit 110011. Okay, in that case, you transmit like 5 volts, another 5 volts. 0, 0, 1, 1. Okay, you basically transmit like this. But from the receiver point of view, receiver cannot figure out if this is a 110011 or if this is just 101 with a slower clock. In this case, what the transmitter transmitted is that the symbol duration, the sample duration is, for example, it's like 1 microsecond. But from the receiver point of view, receiver is receiving 2 microseconds of 1, 2 microseconds of 0, 2 microseconds of 1. So receiver doesn't know if this is 101 with a slower clock or 110011 with a faster clock. The receiver cannot figure out. So there's an ambiguity here. Okay? So we cannot communicate because the transmitter transmitted this one, but receiver is thinking that this is received, so that you cannot do communication. And not only that, we have only 0 and 1 like this. So since there's no clock, what happens is, if the transmitter is doing nothing, let's say the transmitter is not doing anything. Transmitter is not doing anything. This is not transmitting any bits. However, this is just a line, just a wire. So you may have a certain voltage, like a leak voltage, right? You may have a voltage always. So let's say this is a ground voltage. Let's say 0 volts. Since you are not transmitting anything, is it like really the transmitter is not transmitting anything, or maybe transmitter is transmitting all 0. Which one is the case? We don't know, right? Or put it another way, let's say receiver is always getting 5 volts. Just getting 5 volts all the time. Is it the case where the transmitter is always transmitting 1? Or transmitter doing nothing? Which one is the case? We don't know, right? So we don't know. So that's why if you don't have a clock, okay, then we have a problem. If there is a clock, let's say, if there is a clock, we have a clock like this. Then you transmit the data based on the clock. So whenever you have a clock and you have a data, then receiver knows, what is the sample duration and also what is the bits for each of these things, right? It is very clear because we have a clock, okay? It's very clear, but in this case, we have no clock. So it's difficult to find out. So we need to investigate a little bit more on the asynchronous communications. In 8051 chip, we have 2 pins called RxD and TxD. These 2 external pins are used for UART, or asynchronous communications with external device. Okay, we have some external device, and we want to have some serial communication with external device. For example, like PC. You have an 8051 board. We have a PC right there. So you connect like a USB connection. And using the RxD and TX pin in 8051, we want to do serial communications. And this picture shows you what happened in the hardware of 8051 processor. As you remember, we have register called SBUF. Okay, SBUF. But it looks like we have 2 SBUF, one in here and one in here. But one SBUF in here in the receiver side is read-only from your side. Okay, you are using the 8051. But in this case, it's read-only because this is a received pin. For 8051, it is a received pin, which means that someone else is transmitting to you. So you are receiving it. Since the data is coming to you from the external device, you are receiving it and receive the letter like A, B, C, those character now goes into SBUF. So what you need to do, you just simply read it. Okay? Therefore, this is read-only. This is just read-only. Whereas when you transmit, you are transmitting. Okay? So if you want to transmit like a letter C, then you are writing C into this register. Okay? Writing C into here, then it will be transmitted by the hardware. So for the hardware, we have looks like 2 SBUF registers, but in fact, this is just 1. Because this is read-only, this is just write-only, so just 1 address is enough. If you write C into SBUF, it's the same address. These 2 are same address. So if you write C into the SBUF, that goes into here. If you read some value from SBUF, you're going to read it from here. Okay, read it from here, writing here. So these 2 actually have 1 address. Okay, so this is in fact just 1 address. But hardware, it works as this way. In order to control the serial communications, we have a register called the SCON, Serial Port Control Register. Remember that for interrupt hardware, we have some of the interrupt controller, right? We have some of the registers. For example, IE, interrupt enable, or interrupt priority, right? For that interrupt hardware, we have some of the registers. We also have a timer hardware. For timer hardware, we also have other registers, right? T-mode, T-con, timer control, timer mode. Similarly, in the serial port, serial communication hardware, we have SCON register, right? So for software, for assembly, we need to write some value in here in SCON register in order to control the serial communication hardware block. So we have 8 bits. So the first two at MSB, including MSB, we have SM0, SM1, 2 bits. These 2 bits are used in this way. If you write the 0, 0 into these 2 bits, now we are selecting the mode 0, serial communication. So we have 4 different modes, serial communication modes. Mode 0, mode 1, 2, 3. Okay? We have 4 different serial communication modes. Remember that in timer also, right? We have 4 different timer modes. In serial communication also, we have 4 different serial communication modes. And each one has each mode is different in the sense that each mode has a different baud rate. This is called a baud rate. What is a baud rate? It's like a speed. You know, how fast you can transmit. That's speed, data rate, or baud rate. So each mode has a different baud rate and has a different characteristics. Like mode 0 is synchronous and half duplex, and mode 1 to 3 are asynchronous. It is more popular to use asynchronous, but I'll tell you the details in the next slide. I'll tell you about this one a little bit later, but REN, this is the receive enable. Okay, remember that why we need this receive enable. For transmit, you don't need any transmit enable because only when you want to transmit, you are going to write the value. Right? You want to transmit letter C, only then you are writing C into SBUF. Otherwise, you are not writing. So you can control the transmit side because you transmit. However, in the receive side, someone else is transmitting to you. So what happened is that I don't want to receive anything, but someone is transmitting to me. So that's what can happen, right? In order to avoid such case, you have a receive enable. If you make this bit to 1, that means I want to receive. Okay, I want to enable my receive block. But if you want to have 0 here, that means I don't want to receive anything. Someone maybe is transmitting to you, but I don't want to receive it. Okay, so your serial communication hardware is not activated. It's not working. Even though someone is transmitting, maybe that's discarded. Okay, so that's what it is. And TB8, RB8, I'll tell you this one in the next slide. TI-RI, this is interrupt flag, receive interrupt, and transmit interrupt flag. And remember why we need this? In order to understand these things, let's go back to the previous slide. We have to understand software and hardware. This is hardware. Okay, this is hardware. So let's think about the transmit side. In transmit, if you want to transmit letter C, then software basically have to write C into this buff, SBUF register. Right? How can you do it? How can you write the letter C into SBUF? Simply, you want to do move SBUF like this, right? This is what you do. Copy my letter C into SBUF. This is the same as writing. So this is all I need to do. From software perspective, that's all I have to do. So when I do this, then I'm expecting that the C will be delivered. C will be transmitted. Now let's think about the hardware. So hardware point of view, when you run this software instruction, then the letter C goes into this hardware register. Then what do you need in the hardware? Hardware basically read this value. Okay, C is not 1100. Right? If you do that, then C basically goes into here with ASCII mode. Okay, ASCII type. Okay, I don't know what is the ASCII number for C, but it's like 1111. It's 8-bit basically. So what the hardware has to do is that read these 8 bits, okay, and then transmit one bit after 1 bit. We have 8 bits, right? So you need to transmit 1 bit by 1 bit. But it's not just simple transmitting like 1 bit by 1 bit. You need to make packets like this. So that's what hardware has to do. So I'll tell you details about this one in a minute. But what the hardware has to do is that hardware simply read these 8 bits and make a certain packet, okay, make a certain shape, and then transmit one after another. So definitely hardware probably takes a little bit of time to make a packet and transmit 8 bits one by one. It probably takes a little bit of time, right? So you need to wait. The software has to wait until the hardware finishes all the transmission. After the hardware finished transmitting these all 8 bits, now then it's time to write next letter, right? Let's say you want to transmit C, and also let's say you want to transmit D. If you want to transmit C and D, 2 letters, right? You should not do this. If you do this, then the software runs this one, and immediately after you are writing the D value again. But you need to have a little bit of delay between these two. Why do we need delay? Because hardware now has to transmit C. Hardware needs some time. But you don't know how much time the hardware needs, right? So that's why we are going to use the TI bit, okay? TI bit in the SCON register. So like this one, right? TI bit. When the hardware, when you write this command, then C value goes into SBUF. And as soon as it goes to SBUF, now the hardware reads it from SBUF and make a packet and transmit. And if the hardware, when finished the transmission of all the C value, then hardware make this bit to 1. So what the software has to do is that you execute this line, write the value into SBUF, and then watch that and wait until this becomes 1. You need to wait. Software has to wait until this one becomes 1. Okay? Just watch it. And if at some point, this one becomes 1, then now it's time to do this. Because that bit becomes 1 means that hardware already finished transmitting C. That's what you need to do every time. That's the transmit side. Let's look at the receive side. In the receive side, similar. In receive side, here's what happened. From some external device is transmitting value C to you. So that value comes to your processor, and that C automatically goes to SBUF by the hardware. In this case, what hardware has to do is that hardware basically receiving a certain packet, including C. Okay, including C, it's a packet. Again, you are transmitting packet, so of course you are receiving similar packet. You receive that packet, okay, and then from this packet, the hardware basically receive that and convert the packet into the value C. Okay, you need to do a conversion from packet to C, the value C, and put that value into here in SBUF. That's what hardware has to do. But that kind of process, receiving the packet and recovering C and put that C into the SBUF, that takes time. Okay? Hardware cannot do that immediately. Hardware needs to have a little bit of delay to do all that process. So once the hardware successfully write C value into SBUF, then the hardware will make the RI bit to 1. Okay? So what the software has to do is watch it. Watch this RI bit. Initially it's 0, but at some point RI bit becomes 1. Then what do you need to do in software? Once this becomes 1, now it's time to go to SBUF and read. Because hardware already finished, received it successfully, and put that value into SBUF. So your value is ready to read. Okay? It's ready at the SBUF. So that's what they mean. Once this becomes 1, your value is ready. So it's time for you to go read. Now go there and read the value from SBUF. But what you need, how can you read it? Same, right? Basically same way. You can simply read it this way. You are copying the value in the SBUF into my accumulator. This is simply read it. Because I have a value in here, and I copy this value into my accumulator. Once you do this, right, then you can do whatever you want with this A, with the value into A. Because I copied this value, the value in the SBUF, into my accumulator, right? So the value in the accumulator is the letter you received. You should not do this, right? Because in this case, you're reading SBUF, and after that, you are again reading it. Hopefully, what I was trying to do, in fact, is that I was reading one letter, and I was trying to read next letter. That's what I was trying to do. However, that's not going to happen in this case. Because when you read it, right, then hardware, again, needs a little bit of delay to receive the next letter. And it's a packet, so you convert the packet into a letter and put the letter into the SBUF. That takes time. So hardware needs a little bit of time to prepare all this. Once the hardware has its delay, okay, to receive the letter, and as soon as hardware finished that kind of process, hardware make this one. So what the software has to do is watch this, and once this bit becomes 1, then go ahead and read this. Go ahead and do this. Okay, once you do this, again, then you have to watch it. So between these two here, now you have to watch it. Watch the TI until this becomes 1. Okay, that's what you need to do. Once the RI becomes 1, now you can do this again. You do this again you have to watch RI. It becomes 1, then again you can read it. Okay? That's what you need to do. It's like an interaction between the hardware and software. Hardware basically do its own job, and software, we simply read it or write it. But these two guys, the software and hardware, needs to communicate using these bits. That's how we do it. Okay? It's pretty simple, actually.
Then after reading the value in SBUF, the RI, the value of RI equals 0?
No, you need to clear it. Yeah, that's a good point. So when you are basically watching this bit, right? And when you watch this bit becomes 1. Then it's time to read the next bit, next letter from the SBUF. Once you do that, you need to clear this. No one will clear this one, right? If this one stays 1, then you cannot distinguish the next letter, right? So you need to make this 0. You need to clear this bit. You need to do it. Same here. TI, RI, you need to clear it. So every time you read it, and every time you find that these bits becomes 1, then first you need to clear. Then do the next, then read from SBUF. So now let's look at the packet or the data, how the data is transmitted over the wire. This is the case with mode 0. What is special about mode 0? Mode 0 is a synchronous communication. Come back here. See that when you have a mode 0, you put 0, 0 here. That means you are using mode 0. In case of mode 0, it's a synchronous communication, which means that you have a clock. See here, you have a clock like this. We have 2 pins, right? What pins do we have? We have RxD, TXD. We have 2 pins. So with the 2 pins, TXD pin, we are going to use as a clock. For RxD pin, we are going to use that as a data pin. Okay? That's how you use in mode 0. TXD, we're going to transmit clock. In RxD, we are going to transmit our data. Once you do that, this is what you're going to see over the wire. Okay, over the wire, you're going to transmit in clock like this. And for the RxD, you're going to transmit a certain data. It's like 1010. So that's what happened in the mode 0. However, the mode 0 is not that popular. Okay, as I said, there's a little bit problem of delivering the clock into the long distance. Okay, but if this clock is not delivered to the receiver, then there's no communication in this case, because your communication depends on the clock. So if the clock is gone, then your data communication is gone. So this is not a good way, actually. So the better way, or most popular way, is to use mode 1. Okay, let's look at the mode 1. In mode 1 and mode 2 and 3, all the other modes, it is asynchronous. So we have some problem in asynchronous communication. In asynchronous communication, as I said, there's no clock. So we cannot distinguish 110011 or 101. We cannot distinguish in this case. And not only that, let's say if the transmitter always has a 5 volts, then receiver is confused. Okay, I have always 5 volts. Maybe transmitter is transmitting all 1. Maybe. Or maybe not. It's a little bit confused. Okay? So that's a problem in asynchronous. Therefore, and also, here's a case. Let's say in asynchronous communication, typically, right, these kind of data pin, you have a 5 volts when you have nothing. Okay? What do you call that, typically? Think about the microprocessor. Remember that on the first week or second week, we talked about the active low. Remember, active low? A lot of the data pin in the digital processor, digital systems, you use active low, which means when you have nothing, when you are idle, you have 5 volts. Same here. In this case, over the data pin, if you are not transmitting anything, it always like 5 volts. Like 5 volts. Right? So now, let's say that this is the data pin here. And right now, we have a 5 volts here in the data volts, in the data pin, because transmitter is doing nothing. We are not transmitting anything, so therefore, this wire has a 5 volts. Now suddenly, transmitter wants to transmit some value. Let's say I want to transmit 1100. Okay? Suddenly, I want to transmit. How can you do it? Maybe if 111 corresponds to 5 volts, 0 maybe is a 0 volt. In that case, we have a problem because this wire is already 5 volts. When you do nothing, it's 5 volts. So we are already 5 volts. But we want to transmit 1. 1 is 5 volts. So I want to transmit 1. So therefore, I want to transmit 5 volts. But this is already 5 volts. So I cannot, the receiver never knows. You cannot distinguish. So certainly this is a problem. So asynchronous, we have many problems like this. Therefore, that's why we need to have, packetized the data. Packetized. So I'll tell you what that means as a packetized. Let's look at here in mode 1. When you compare this snapshot of mode 0 and mode 1, we see a little bit of difference. The difference is that in mode 0, when you transmit 8 bits, then we have only 8 bits. From D0 to D7, these are just 8 bits. Okay? You only transmit the data, 8 bits of data, because we have a clock. However, in mode 1, we have no clock. So what you need to do is that this is the first bit, second bit. So you are transmitting bit 1 to bit 8 bit. But in addition to 8 bits, we need additional one. called the start bit. That's the additional one. It's like a header. Okay, header of your information. Since you have additional bit called the start bit, we can call this whole thing as a packet. Okay, in this case, and also additional thing is that we have a stop bit at the end of it, but this stop bit is same as 5 volts. So you cannot distinguish stop bit with the idle state. In idle state, you have a 5 volts, but stop bit also is a 5 volts. So it is hard to see, hard to distinguish. But anyway, including stop bits and also start bit here, the total is 10 bits. These 10 bits we call as a packet. Okay? We call this whole thing as a packet. Now then, let's understand why we need a start bit. Okay? Here we have a start bit, and let's understand why. So as I said earlier, we have this problem. In idle state, this line, we have 5 volts. But suddenly I want to transmit 1100. So we have a problem in this case. Therefore, whenever you start transmission, okay, whenever, let's say you want to transmit this 8 bits, when you transmit this 8 bits, you always have to have a start bit right here. So what do you need to in start bit? Start bit always is 0. As you see here, this is 0. So when you have a start bit, let's say I want to transmit 11000110. Okay, that's what I want to transmit. In that case, what they do is that we add a start bit right here. Basically, I'm transmitting this way. Okay, we have a start bit right here, and actually start bit is same as a 0, same as like a 0. So what you do is that when you transmit this one, you first transmit start bit. Therefore, in idle state, this is 5 volts, but suddenly it goes down to 0 because of start bit. We have a start bit. And then followed by 1100. It's 5500, something like this, right? So these 8-bit, okay, 8-bit has to be preceded by 0. So 0 has to come first. So what is the receiver looking for? What the receiver does is that when the receiver receives 5 volts, generally that means idle state. So receiver is doing nothing because the receiver knows that 5 volts mean idle state. So what the receiver looking for is that suddenly these 5 volts drops to 0. It's like an edge, high to low edge, right? Suddenly edge starts. That means what? Now its data is coming. Okay? My data is coming because I have an edge. So this is like edge detection. So receiver is detecting edge. That's the reason why we have a start bit. Okay? So this is an indication. This basically indicates, this edge basically indicates that, okay, my data is following. I'm basically bringing my data, 8-bit data. That's what you do. So it's very simple, right? The receiver is just watching and waits until to detect edge, the high to low edge. That's all you need in the receiver. As soon as you can detect the edge, like this edge, then now you can decode all the 8 bits. However, we have one more problem. Okay? This is clear, right? But we have one more problem. Let's say I'm transmitting this data. Okay? In that case, my start bit is always 0. This is always 0 because we need to do edge detection. Start bit is always 0. But actually my data, 8-bit of data is 0, 1, 1, 0, 0. So looking at the data pin, what is going to happen is you have a start bit. So you have edge, of this much, followed by 0, followed by 1, 1. So we have a 0, 0. So now we have the same problem. Same problem as before. From the receiver point of view, looks like I have a start bit, so I have a 0 here. But we have another 0, right? And we have a 1, 1, 0, 0. So the receiver now is confused because let's say initially what the transmitter tries to do is 1 microsecond of bit duration. Everything is 1 microsecond. That's what the transmitter was originally transmitting. But let's say receiver is confused because the receiver may think that, okay, looks like this whole thing is a 2 microsecond start bit. And maybe this guy is transmitting 2 microsecond of 1 followed by 2 microsecond of 0. Maybe this is the case, right? From the receiver point of view, I never know. It could be like this one, or it could be this one. We don't know, right? So that's why in asynchronous communications, what you need to do is that we have to make an agreement between the transmitter and receiver. So I'll show you one example. Look at here. This is a PC, right? Just Windows PC. In the Windows PC, if you go to here in the communication, we have a hyperterminal. Maybe some of you have used this before, hyperterminal. This one has to be configured. Okay, this is the serial communication. Let's say you have a 8051 board, and you connect your PC with the 8051 board using serial communication, serial port. Then you can do actual communication using this UART the same way. But look at here. In order to do this asynchronous communication, what you need to make sure is that you have to set this baud rate. Let's see. Yeah, you need to set this baud rate. Okay? That's why in asynchronous communication, you have to set this baud rate. So this is like an agreement between the transmitter and receiver. What is this? This is a number of bits per second. 2400 means I'm going to transmit 2400 bits per second. So this one basically means that I'm transmitting almost 1 million bits per second. This one I'm transmitting only 100 bits per second. Very slow, pretty fast. That's what it is, right? But what you need to do is that you need to make sure that, let's say, if you want to use like 2400, then you need to set in the PC side, okay, I'm going to use 2400. And also in the receive side, I'm going to use 2400. Okay, you need to configure at both sides with the same baud rate. Right? If you set it like 9600 into the transmit side, in the PC side, and you set it like 2400 in the 8051 in the board, in the receive side, you cannot communicate. Why? Because of this problem. So let's say in both sides, transmitter and receiver, you need to set it the same speed. Let's say we set it like 1200 in both sides. Okay, in both sides, 1200. So you have a PC here. In PC, you can run the hyperterminal like this. This is called hyperterminal. And in the hyperterminal, now you set it to 1200 bps. Okay, I'm going to use a 12 bps. And PC is connected with our processor. And inside here, we also have to set it like a 12 bps, 1200 bps. We have to make the same. Once you do this, right, 1200 bps, then what does that mean? What that means is within the 1 second, we have 1200 bits So how much is the bit duration? In 1 bit duration, how much? How much is the time? It's like 1 over 12 seconds. So the 1 bit duration is almost like an 800 microsecond. Yeah, right? So this is same as this one is 800 microsecond, or almost. Okay? So since the transmit side and receive side agreed, both sides agreed to use the same speed like this, now what we know is that 1 bit duration is fixed to 800 microsecond. So therefore, receiver is not confused anymore because receiver knows what is the duration. This problem happens, you know what I'm talking about, right? This problem happens because the receiver doesn't know anything about the bit duration. Receiver is receiving 110011, but receiver is confused. Maybe this is long 1, long 0, long 1. Okay? The receiver is confused because the receiver doesn't know about the bit duration. But once you agreed like this, then receiver now knows the bit duration. For example, like 800 microsecond in this case. So there's no confusion. It's pretty clear. Okay? So in asynchronous communication like this, what you need is that you need to make an agreement at both transmit and receive side. What would be my baud rate? This is called the baud rate. You need to make sure that we have a same baud rate at the transmit and receive side. Not only that, you also have to make sure that you have to have a start bit. Because without start bit, again, it's a receiver can be confused. Right? So you need to have an edge detection at the receive side. Therefore, we need a start bit. And because of this possible confusion, we need to have agreement on the baud rate. That's what you need in here. That's how we do communication. There are two other modes called the mode 2 and mode 3. In mode 2 and mode 3, the basic idea is the same. It's basically the same idea. Only difference is that compared to the mode 1, this one has 9 bits. And including start bit and stop bits, total is 11 bits. In the previous mode 1, remember that we have 8 bits here, but we have a start bit, stop bit, so total 10 bits. Compared to that, in mode 2 and 3, we have one more bit here, bit 9. And this description basically tells you what we do in the bit 9. But to describe that, we also have to understand SM2. What is SM2? This is SM2. So somehow SM2 bit is related with the bit 9. So these are how it works. In the mode 0, it's ignored. It doesn't work. But so it is not important. In mode serial data mode 1, this is how it is used. Okay, it's a little bit complex, but and it's not really popular. But let's look at it. If you use mode 1, then SM2 is 0. Then the data word is loaded to SBUF regardless of any stop bit. So in this case, the stop bit, they are not checking the stop bit. That's what it means. Stop bit, here's the thing. In start bit, you always have a 0. Start bit is always 0. So therefore, when you are in idle mode, you have 5 volts. But suddenly, when you transmit the data, it goes down to 0. That's what you do in the start bit. Stop bit, actually, you have to go back up to the 5 volts, right? Because we are going back to the idle mode. You are finishing the transmission. We already done finishing, right? The transmission of 8 bits. So it's time to go back to the idle state. So therefore, the stop bit always go back up to the 1 volts, the 5 volts. Okay? So therefore, the stop bit always 5 or high. Let's call this high. So stop bit means high. A start bit means low, always. But when you have SM2 bit equals 0, then you are not checking the stop bit. So even though the stop bit goes down to 0, which is error case, you don't care. You are not checking error. That's what they mean. But if you have SM2 bit to 1, then you are checking, right? So stop bit may go down to 0. That's actually error case. So when you have an error, then, oh, this is error, so I'm going to drop. I'm going to drop the whatever letter I receive. Because when I receive a letter, let's say I'm a receiver. You are receiving these bits, right? So first thing to do is that you are checking the edge. Since you are receiver, you are checking this one. And once you detect the edge, high to low edge, now you start to receive one by one. I receive it. Until you see the stop bit. And the last thing to do is that you need to check if the stop bit goes back to 5 volts or high. But think about it. Let's say there was an error. So you checked, you received the 8 bits, and now it's time to receive the stop bit, but suddenly the stop bit is 0, still 0. That's error, right? Because at the stop bit, you are expecting a 5 volts or high, but you are still seeing low for the stop bit. Then actually that means error. So when you have an error, what do you need to do? Then I cannot believe that what I received so far, maybe what I received so far maybe is wrong. Because if everything is correct, then stop bit should go to high. But I detect that stop bit is low, so maybe what I received so far, 8 bits, maybe is garbage. So what do you need to do? Drop it. That's what you need to do. That's what you're doing when SM2 equals to 1. But what do you do in SM2 equal to 0? That means I don't check. Maybe stop bit go down to 0. Maybe stop bit is 1. I don't care. Whatever I receive, I just take it. Okay, that's what it means. The same way, when you are in a mode 2 and mode 3, it's a little bit more complex because in mode 2 and mode 3, we have 9th bit. This one, right? We have a 9th bit. So depending on the 9th bit equal to 1 and SM2 equal to 0 or 1, you have these different modes. Sometimes you have an interrupt, sometimes not interrupt, and things like that. But this is a little bit more detail. And as I said, most of the time, we are using mode 1. This one, most of the time. Okay, so if you have an interest, then you can take a look at these things. Now, there's another register called PCON, Power Mode Control. Sounds like PCON is nothing to do with the serial communications because this register is related to other hardware block, power mode control block. However, one bit here, the MSB bit, this bit actually is related to serial communications. Here the S mode, this is a serial baud rate modified bit. The reason that this only one bit goes down to this register is because that in this register we have only 8 bits, but I need 9 bits. In serial, this is the control register for serial communication hardware, right? In order to control the serial communication hardware, I need 9 bits, but I only have 8 bits. 9 bit is a little bit, is a bit strange number. We have 8 bits, so you have one remaining bit. That one bit now goes to another register, this register. So this one bit in this register is also used for serial communications. And I'll tell you how it is used. Let me give you one example here. And this example basically shows you how the serial communication works in asynchronous communication, the mode 1, because mode 1 is the popular one. So here, as you see here, the receive D, typically this data pin is high when no data is received. Okay, when you are in idle mode, idle state, you have high. And receiver basically waits for the 1 to 0 transition, high to low transition. And whenever you have this transition by star bit, then now it's time to receive the following 8 bits. Okay? Since you do the edge detection, now you still keep receiving until you receive the 8 bits, right? Then how do you know how long the bit duration is? We already had the agreement, okay? The transmitter side and receive side, we already had the agreement about the baud rate, as I said earlier, right? Right? The transmitter receive side, we already have the agreement like a 2400 bps or baud rate, or maybe 1000 bps, something like this. So since the transmitter and receiver side both of you agreed with a certain baud rate, we already know what is the bit duration. Yeah? So what you need to do is just transition high to low, and then since we know the duration or bit duration, we can actually receive the following 8 bits, and then the stop bits goes back to 5 or high, then it's finishing. Now you receive these 8 bits, and these 8 bits now goes to SBUF. Okay, these 8 bits goes to SBUF. And when the hardware receives this, and these 8 bits goes to SBUF, and then now you have RI bit to 1. Interrupt, right? RI bit. And software now reads it, SBUF. Then this value now goes to my software register. That's the process. This is an example for transmitting data. Okay, let's say we want to transmit. In order to transmit the value, let's say I want to transmit the value 23. So what do you need to do in order to transmit this value? Simply you're writing this value into SBUF. As I said earlier, right? This is simply copying. From software point of view, what I need is just to write this value into SBUF. That's it. That's what I need in software. Once you do this, now what do you need to do? You need to watch the TI. What is this one? Jump, not B. If this bit is not 1, then you are jump to this one. What is this one? This one basically means its own. Its own. Okay, it is jumping to its own. That's what they mean. Okay, it's just jumping to its own. What is its own? This one. This one. It's looping within one instruction. It's jumping to my own. Okay, that's what they mean. Because what I need to do is just watching. That's it, right? So you are basically waiting until the TI becomes 1. Once the TI becomes 1, now what do you need to do? You need to clear TI. Then you are transmitting, or you are copying next value. And once you do that, again, you have to do this one, JNB, TI. Okay, you need to do it again. So this is how you do it in transmitting. Let's look at in receive side. Whatever you receive here is that, let's say what you need to do is that you need to first set B, receive enable. Okay, because you want to receive. You need to enable the receive side. And then you are watching the RI until the RI bit becomes 1. This is the same one, right? You are basically jumping to its own. You basically watch the RI until this RI becomes 1. And as soon as RI becomes 1, that means what? Hardware received this one. And this 8 bits now is ready in the SBUF. That's what they mean, right? When RI becomes 1, that means this is already in the SBUF, you are ready to read. So once this RI equal to 1, now you are jumping out. And what do you need to do? You need to clear first. Okay, RI has to be cleared. And then simply read it. Because hardware already have that. It's for your software job to read it. That's what you're doing in receive side. This picture and this slide shows you how to set baud rate. It is very important to set the baud rate because of this problem. Okay, so we need to set the baud rate. In PC side, as I show you, I can open the hyper terminal and I can set it by clicking the menu in the hyper terminal in the PC. However, your PC is connected with the 8051 our board, and how do you set the baud rate in your board? In 8051, in our processor, how do you set your baud rate? We want to set like 2400 bps or something like this. How do you set it? This is how to do it. Okay? So this slide shows you how to set baud rate, speed of your bit transmission. So let's take a look at it. This one all starts from timer. Okay, so what it means is, remember that first we learned the interrupts, and after that we learned the timer. Now we are learning serial communication. It's all related. Okay? You need to use timer in order to use serial communications. Why do you need timer? Does anyone give me any reason why you need a timer in here, in serial communications? Simply, right? Simply because that if I set my baud rate into 1200 bps, okay? If I set it like this, that means my bit duration is 800 microsecond. So how does microprocessor know 800 microsecond? We never know. There's no way we can say that 800 microsecond. How do you know? In order to measure, this is like a delay. Every time you have a 800 microsecond, I want to transmit 1 bit. Every 800 microsecond, I want to transmit 1 bit. So how do you measure this delay? We need to use timer. In order to measure accurate time, for example, 800 microsecond, we need a delay. We need a timer. Okay? So that's why we need a timer. So setting the baud rate, we need a timer. So now let's take a look at it. This timer overflow, remember this TF1? This one comes from timer. And what is the condition you have timer overflow? What bit is 0? Yeah, so you have a timer register called the TH and TL, right? And TH, TL, you have some initial value. And as soon as your pulse train comes in, every time you get a pulse, the value inside in TH and TL is incremented, right? And as soon as a TH and TL becomes 0, it's all 1, 1, 1, 1, 1, and 0, then you see this overflow. Okay? When you have overflow, you are basically dividing by 32. What that means is, based on your timer, let's say you design your timer such that I want to have overflow in 1 microsecond. Every, let's say every 1 millisecond, let's say. Okay? So I design my timer to have an overflow in every 1 microsecond, every 1 millisecond. Let's suppose that's the case. So in every millisecond, I have an overflow. 1 millisecond later, I have another overflow. Something like this, right? In that case, that's what happened here. Right here, you get overflow in every millisecond. But since you are dividing by 32, what that means is right here, you are getting a pulse in every 32 milliseconds. Simply dividing it is counter. It's counter. You're basically getting 1 overflow, 2nd overflow, 3rd one. In every millisecond, right? You have a 1 overflow. Okay? 1, 2, 3, 4. And you get a 32 overflows. Then now you have only 1. Every time you have a 32, you have now 1. Okay? So right here, you may have an overflow in 1 millisecond, every 1 millisecond. Here, in every 32 milliseconds. It's slower here, right? That's what it means. And this hardware basically means that right here, it's every 16 milliseconds. So this is actually a little bit faster, right? This case, you have the clock coming in every 16 milliseconds. Here, every 32 milliseconds. So this is twice faster than this one. So how to control that? How to control this one or this one? It is controlled by S mode bit. And where is S mode bit? Right here, S mode. So that's where you will use this bit. This bit may be 0 or 1, depending on this bit. This is hardware, basically. Depending on that bit, we may be using this hardware or maybe use this hardware. Now, based on that, this is a baud rate clock. This is our final output. Okay? Let's say if we want to have 1200 bit the baud rate, BPS, then as I said, 800 microsecond is what we want. We want to have 800 microsecond right here. Right here in the clock, we want to have 800 microsecond. So how can you do it? Let's say I want to have 800 microsecond of clock right here, right? But since we divide by 32, what clock do you need here? Okay, so here's the thing. Right here, at the output, what they mean is you have some clock, baud rate clock. That baud rate clock looks like this. Right? Baud rate clock looks like this. But this clock, one clock duration, this is a baud rate clock. One clock duration is, as I said, 800 microsecond. That's what we want right here. Because we want to use 1200 PPS. So therefore, we want to make this clock like this. This is what we want, right? Because this one is same as 1200 PPS, right? So this is what we want. In order to get this here, okay, in order to get this here, and suppose now we use this one, this hardware, okay? Let's say we set it S mode equal to 0. This is what we have in hardware. So what do you need here? Huh? Right here, you need a delay of 800 microsecond. So here, what you need is that you're going to need 800 divided by 32 microsecond. So it's almost, how much? It's like a 26 or something like this, right? This is the delay you need right here. Why is that? Let's say we have a, it's not 26, right? It's not 26. It's almost like a 2.6 microsecond. So you need a 2.6 microsecond here. Why? Think about it. Now we have a overflow in every 2.6 microsecond. 1, another 2.6 microsecond, 2, another 2.6 microsecond, 3. So you have a 32, which takes 800 microsecond. Then you have 1. You know what I'm saying? So you have a 32 of overflow. That now then you have a 1 clock output right here because of this 32 division, right? So you have 800 microsecond here. That means right here you have a overflow in every 2.6 microsecond. Right here. Now then, how can you make a 2.6 microsecond here? Let me see. I think this number is a little bit. Let me see. Is it 800 microsecond, right? 1200 is same as 800 microsecond. So 800 microsecond divided by 32. Is it 26? 25? Is it 25? 25? let me see, 25. Yeah, okay. So what that means is you are going to have a delay of 25 microsecond right here. Okay? You want to have an overflow every 25 microsecond. So how can you do it? Once you do that, once you figure out that, okay, I need an overflow, timer overflow every 25 microsecond, now it's all the timer thing. Forget all this. Forget all this. Now let's focus on the timer only. Let's focus on the timer. Okay? So let's try to remember what we learned in the timers. How can you make a timer overflow in every 25 microsecond? How can you do it? Suppose we are using a if you remember the block diagram we saw the last week, we had a block diagram like system clock, system frequency, which is 12 megahertz. That goes into divide by 12. We had this, right, earlier. So now you get a 1 megahertz of clock frequency, right? This 1 megahertz clock goes into the timer. And this right here is not like the pulse train. This pulse train has the clock frequency of 1 megahertz. And in this case, the 1 megahertz clock, what is the duration of the pulse? It's 1 microsecond. So which means that from your original clock, after you go through the division of 12, right here, your pulse duration is 1 microsecond. Every pulse is 1 microsecond. And what do you want to do? We want to count 25 microsecond here. So what do you need? Original input to the timer is a pulse train. Each pulse is 1 microsecond. Here, we want to have an overflow every 25 microsecond. So what do you need? What you need is that inside the counter, you need to count only 25. As soon as we have a 25 pulse coming in, I have overflow. And every time you have a 25 overflow, that's what you need in timer, right? So what's going to be your initial value in that case? Think about the timer. What's going to be initial value? Okay, it's important to remember, how to set the initial value. Okay, that's one of the very important things in the timer. Okay, when I say important, that probably is a exam, right? Remember? So let's say we have a timer here, TH. I want to count 25. So what will be the initial value? 256 minus 25. 231, something like this, right? This would be the initial value in order to make 25 microsecond of delay. And once we have a 25 microsecond of delay, now then we have overflow in every 25 microsecond, but we have a division of 32, so you have a 800 microsecond here, and that's what we want. Actually, this is not exactly 800, because if you do the division of this is a little bit higher than, I think it's 830 something, right? So once you use that 800 something, then I think this is a 26 microsecond. So therefore, when you have a 26 microsecond here delay, it's 26. So your initial value is 230. That's what you have here, 230. So what I just said is a logic. I just explained how it works in hardware. But mathematically, this is how you calculate. But just looking at this mathematics, it doesn't really make sense to you, right? It's a little bit, it doesn't make sense. So important thing is to understand the hardware logic, how the hardware works. And put this one in mathematics, that's how things work. So let's look at the mathematics a little bit. This is the mathematics. So let's first look at the system frequency. What is the system frequency? 12 megahertz. Original one, this one, 12 megahertz. And inside the mathematics, we have system frequency divided by 12, Why do we do a division of 12? Because of this. We have a division of 12. And look at this one, 12 times 32, right? So we are still dividing with the 32 because 32 is on the bottom, right? So why are we dividing by 32? Because of this. Actually, this equation is the case where you use this hardware. Okay? So that's why you are dividing by 32. So this 12 comes from that 12, and this 32 comes from this 32. And now you are again dividing by your own baud rate. So in our case, in our example, I want to use a baud rate of 1200. So you are putting the 1200 here. And why are we doing this subtraction? 256 minus this. Why are we doing this? Because that's what we did in the timer, right? Remember that when you set the initial value in the timer, you always do this. Remember that? So that's why we are doing this. So this calculation basically tells you what would be my initial value if I want to create the baud rate of 1200. This looks like a very simple calculation. Looks like very simple, right? However, you need to understand the logic. There is a timer here, and timer is using a system clock frequency as the input. We have a division of 12, and that pulse goes into either here or here, and that eventually creates the baud rate, and that baud rate will be used for our serial communications. But in this case, look at the timer, right? We have 4 different timer modes. Which timer mode do you want to use? We have 4 different timer modes. For this case, we want to use the timer mode 2. What is the timer mode 2? Auto reload. Auto reload. Why? Because this is the initial value. You don't want to initialize every time. You want to let the hardware to do auto reload every time. That way, you don't have to initialize. So this initial value, 230, this value should go to what register? TL register, right? This value, initial value, has to go to, is it TL? TH. 1 second. Oh, this one, yeah, this one should go to TH. Let me see. Yeah, so we need to write that value, initial value here in the TH. So that way, those are the initial value 230. You want to write it here in the TH. That way, the hardware automatically load this one into TL. And actual counter is this one. This is actual counter. This TH always has just initial value. So this one becomes 0. Then you have overflow. This one automatically loaded and run again. Okay, so that's what you do. So you are basically loading the value in the TH like this. But this is the case when you want to use like a low bit rate, like a 1200 BPS. But sometimes you may want to use a little bit higher baud rate, such as this one. Okay, such as this one. 19,200 baud rate. If you want to use this kind of high speed baud rate, what you want to do is you want to use S mode equal to 1. Why do you want to do that? Because S mode equal to 1 means we are using this one. And if you use this one actually is 2 times faster than this one, 2 times higher clock. So if you need a high baud rate, you may want to use this hardware by setting this bit to 1. So this one basically shows you configurations. Once you use this one, right, then what equation do you need? You need this equation, right? Because instead of 32, you need to use a 16. Yeah. So this is the equation you are going to use in order to calculate the initial value. So this is going to be initial value for you. I think last year in the final exam, one of the question was to calculate the initial value. I'll give you like a baud rate. Okay, I want to have a serial communication with the 2400 bps. What is my initial value in the timer? Something like this. Okay, how do you configure the timer? Something like this. It's easy actually, right? Pretty easy to do it. But that's what you need to understand. So this is how you do it, right? This is a simple example here. This is an example to have a serial communication with a baud rate of 1200 bps. So let's see here. We want to have a clear and set B. This is basically to set the mode. SM00, SM1 to 1, that means we are selecting the mode 1. Okay? So by setting these 2 bits, we are selecting the mode 1. And by T mode, what do you need? What are you doing? We are setting the timer modes. Timer mode to mode 2. And this is the value you have calculated here. Because I want to use the 1200 bps, based on this calculation, I found that this one you need to do it manually. So based on that, I found that this is my value, initial value. So you write this initial value here in the TH, and then what do you need? You run the timer. Once you run the timer, now the timer generates the pulses. That pulse eventually goes to the serial communications. Now, what you need to do later? You just simply do, this case, you're writing the value because we are transmitting. But if you want to receive, then you want to read the SBUF. So these are the steps to do. Looks like a complex, but actually it's not. Steps to transmit a byte. If you want to transmit a byte, you need a timer. Why do you need a timer? Because you need to set baud rate. Setting the baud rate requires a timer. So you need a timer. You need to program the timer. And also you need to calculate the initial value of the timer and also program the timer and start the timer. And once you start the timer, now the timer runs. If you want to transmit some byte, then now it's time to write this value into SBUF. That's all you need. Okay, writing the value into SBUF, then hardware will transmit. So you are basically watching the TI until the TI bit becomes 1. When TI becomes 1, that means it's time to write next letter. So you clear the TI first and go back to 5 and keep doing it. Okay? In receive side, it's the same thing. You need the same timer. In receive side and transmit side, you need the same configuration of the timer because this timer depends on your baud rate. So if you use the same baud rate, step 1 to 4 is the same. Exactly same. The only difference is that in the receive side, what you need to do, you have to watch the RI until this RI bit becomes 1. When RI becomes 1, it's time to read. So when you read it, then of course you have to clear RI first, and then you read it. Then what do you need to do? Again, you have to watch RI until you read the next letter. That's what you need in serial communication. But however, one problem in this case is that in transmit side, it's OK. Because whenever you transmit byte, then you can just write it and watch until the TI becomes 1. However, in the receive side, how do you know when do you receive? In order to receive a letter, you need to watch the RI. But I don't know when would I receive a letter? But I cannot watch it. I cannot watch the RI bit 24 hours, right? I need to do something else. So I cannot only watch it 24 hours. So what is a better way to do receive side? Interrupts. That's why, so far what I just explained is that look at this program. This is an example for receiving data, right? Look at here. I'm basically watching the RI forever. This case, if you run the program like this, then you are watching RI 24 hours. You are not doing anything else. So this is a very stupid program, right? You want to do something else because you don't know when I receive the data. So a better way to do is that for software, I want to do something else, and you want to enable the interrupt. So far, what I explained is the case of no interrupt, but you can also enable the interrupt. Okay, how do you do it? Remember that interrupt block? We have a serial interrupt bit. You want to enable the serial interrupt. Once you do that, just simply you make that bit to 1. Serial in an interrupt to 1. Once you do this, now then what happened is that as soon as we have this bit becomes 1 or this bit becomes 1, then now the hardware gives you interrupt. Okay? So what do you need to do then? We have two of them. So either this one or this one becomes 1, then hardware gives you interrupt. So what you need to do actually is that you have to jump to this is a case with the interrupt. So this is your original program. I enable the interrupt here, right? So what I need to do is that I'm basically running my own program, but suddenly I get an interrupt. Then I jump to my serial communication. This is an interrupt vector. So I basically jump to, this is my interrupt service routine. Inside the service routine, since I get an interrupt, I jumped here, right? When I jump here, because of interrupt, then what do you need to do? First thing to check is that, did I get TI or RI? You need to check that first. Because maybe TI is 1, or maybe RI is 1. Okay, you need to check that first. If TI becomes 1, then what do you need? You don't need to do anything, right? Because TI equals 1 means the hardware finished the transmission, so you don't need anything. But, so you check the TI equal to 1 first, and if the TI equals to 1, then you don't have to do anything. But when you have RI equal to 1, then means what? Now it's go there and read it. Read the SBUF. That's what you want to do inside the interrupt service routine. Okay? So that's what we do here, right? Inside service routine. So that's what you want to do. I think we don't have enough time, but I'll cover a little bit more in the next week and continue next week.